Hello, and welcome to this Richardson RFPD webinar series, a walk around the block, focusing on energy storage systems. In today's session, George Wansum, a business unit manager of supercapacitors at Cornell Dubilier, discusses how double-layer supercapacitors, lithium-ion supercapacitors, and lithium carbide capacitors are viable design options for many energy storage applications. So without further delay, let me turn it over to George to get this started. George, go right ahead.
Welcome to the Cornell Dubilier supercapacitor presentation about energy storage and power density. My name is George Wansum, and I am Cornell Dubilier's supercapacitor business unit manager. I have been with Cornell since 2015, and at that time, Cornell purchased my former employer, Illinois Capacitor. My goal today is to help you consider more design ideas or concepts as it relates to your energy storage applications by using supercapacitors. Supercapacitors and hybrid supercapacitors provide energy density and/or power density that can be used in many applications that batteries or aluminum electrolytic capacitors were traditionally the primary choice of the design. I will compare supercapacitors with battery technology and aluminum electrolytics and compare energy density versus power density. Though supercapacitor industry has made great technological improvements over the last 4 decades, it had been slow in coming during the first 2 decades, from the 70s to about the year 2000, Y2K. Millions of dollars was poured into R&D for supercapacitor technology, but still converting those improved materials and capacitor formats, it was still a challenge to get to a mass production state. Many suppliers jumped into the coin cell manufacturing in the 70s and early 80s, but the application expansion did not take place as they thought. Coin cell technology represented most of the revenues of those early decades, and real time clock hold-up applications were prominent. The advancements did come eventually, and for the last 22 years, there has been much quicker advancements in new product introductions in supercapacitor materials, the packaging of the element, and the ability to efficiently mass produce. If you were to visit a state-of-the-art supercapacitor manufacturing site, you would be very impressed and amazed at the investment and the space needed to produce these capacitors, let alone the automation. Probably the best breakthrough for supercapacitor to come was the immense increase of content of electronics in every facet of our lives, our cars, our homes, our technology at home, game controls. It goes on and on. It is truly exciting to be part of the supercapacitor industry. Well, let's get into it. Supercapacitors, and when I say supercapacitors, I definitely am including ultracapacitors, EDLCs, or electronic double layers, lithium ion and lithium carbon supercapacitors, and coin cell technology. There are other materials out there today too, like graphene. Key points when thinking about supercapacitors is they're rapid, they're reliable, and they're safe. Supercapacitors provide rapid bursts of energy and do so in a very reliable and safe way. It is a good solution. All the types of supercapacitors I have mentioned are reliable, and when used per the manufacturer's recommended guidelines, this technology can provide hundreds of thousands, if not millions, of cycles of discharges, and can have a useful life of 20 years or longer. Supercapacitors and hybrid supercapacitors fill the gap between high energy density provided by batteries and high power density provided by the more traditional aluminum electrolytics. The newer hybrid supercapacitor technologies manufactured today now overlap into many traditional battery applications, giving designers potentially 2 or 3 options for their designs. This is true for power density applications, where EDLC supercapacitors and hybrids now overlap into some of the application space of aluminum electrolytics. The energy provided by supercapacitors is stored electrostatically with no chemical reaction. So in supercapacitors, the electrically charged ions are moving to the plates with no chemical reaction, allowing for little loss. Batteries, however, the ions move, they have to be exchanged over and over again, and this can create loss and inefficiencies and lower life. Supercapacitors also have an operating temperature range of -40 to +85 for EDLC types and -25 to +85 for hybrids. Batteries cannot be used in this operating range at all, and for high temperature range, significantly lower than supercaps, as mentioned before, about +55 C. Supercapacitors provide a very lightweight use. So this is important in many applications that designers are trying to limit the amount of weight content in their equipment. And they are energy efficient storage solutions. Only 5% loss. Supercapacitors have a greater than 95% efficiency. Loss is in heat, but in energy, in joules. Batteries, the loss can be, the efficiency could be maybe 70 to 80%. So the loss is 20 to 30%. This is called the Ragone plot. This chart easily depicts energy density and power density and the 3 technologies. Energy density for batteries, EDLC supercapacitors, and hybrid supercapacitors and aluminum electrolytics. The y-axis is watts, watt-hours, and the x-axis is watts. Watt-hours represents the energy density, and the watts represents power density. What the plot clearly shows is that ultracapacitors, with their sister technology, hybrid supercapacitors, really bridge the gap between aluminum electrolytics and battery types. The diagonal lines are important in that they depict the single charge and the discharge duration. Aluminum electrolytics, which is you can see in the circle down and to the right, is ideal for power density applications like AC to DC switching power supplies. And at the opposite end and up and to the left, you see the high energy density, which is covered by the batteries, lithium, NiCad, and lead acid. High energy density is important for a variety of applications: automotive, robotics, wind pitch control, and many others. In the middle of the Ragone plot are the EDLCs, ultracapacitors, and the hybrid capacitors. Supercapacitors can provide both a decent amount of power density as well as energy density. It's important. There are some applications that need both. Supercap technology today can provide both energy density and power density separately and in the same application. This chart is a nice way to look at the key advantages of each technology. We've listed supercapacitors, hybrid supercapacitors, and lithium-ion batteries. I've highlighted 5 key areas. First, the energy densities, which we've talked about a lot. Supercapacitors, again, not good with energy density. That's the traditional EDLC type. hybrid supercapacitors is in the middle. They start to, especially LCC type, the energy densities are going up and getting closer to battery. And for batteries, especially lithium ion, it's very high. Power densities are high in EDLCs, medium in the hybrids, and medium to low with batteries. The temperature performance, as we spoke, is good with supercapacitors and very poor with lithium. Maintenance, supercapacitors, as mentioned before, maintenance free, hybrids maintenance free, and batteries need to be replaced. Long life for both supercapacitors and hybrids, and relatively short life for batteries. And finally, supercapacitors and hybrids are very safe. There is no thermal runaway for either product, where for lithium ion batteries, it is thermal runaway is ever present and not safe. And it's been in the news a lot. This graph is another way of looking at energy density with batteries, supercapacitors, hybrids. As we again look to the left, we follow a couple of these diagonal lines going down to the right. These are the battery types. Each one that shows going down to the right. And that's the lead acid, it's the lithium. And the useful life is not very long and degrading quickly. The flat line represents all the supercapacitor technology with EDLCs at the bottom, and then lithium ion above that, and then in the middle, the lithium carbon capacitors. It is very flat because it doesn't degrade, and so they can provide their energy for what they were designed to for many years. And this is very important because we should be designing not for what happens initially, but designing for end of life. Where do we want the product to be 5 years from now, 10 years from now? And this is important. Applications classifications. This is, fairly basic. Supercapacitors can be dynamic and static applications. Dynamic refers to constant change of current, power, voltage. They can have wide temperature range fluctuations, and there could be in an environment of vibration. Static is like the real clock applications, where the supercapacitors are charged, they're on hold, and they're performing a function when they're asked to do it. They're not dynamic. Supercapacitor functions. Well, some of the main functions that are out in the electronic industry are main power providers, backup power, and pulse power. Supercapacitors and hybrid supercapacitors are traditionally not used in main power applications. They can be, but that's not their primary place. But they can be used primarily in backup power, providing short-term backup power to put factory equipment or critical applications into a safe mode, or they can be used in pulse power for a variety of applications that you could be for GPS, for data, pulsing applications, smart meters, and a variety of other ones. This chart talks about some of the traditional applications of EDLC and supercapacitors. In the power sector, we have wind pitch, energy storage, bridge power, helping to reduce vulnerability on the grid and providing a greater operating temperature range than traditionally done with batteries. In the automotive, there's the regenerative braking systems for engine start and stopping. There is emergency braking situation applications, battery hybridization, and all this providing lower maintenance, fast charging, and increased battery life. Industrial applications is what has really come to the forefront the last 20 years, along with consumer applications where batteries can be replaced or supercapacitors can be used in the same application with them, providing longer life for the batteries. So in these applications, including consumer, they're safe, they're long life, and can provide good power output. They're used in asset tracking, engine start and stop, bridge power, and material handling, forklifts, and robots. The cell roadmap, if we could go back 40 years, you'd see quite a lot. And again, it was a little slow in coming, but the last 20 years, there's been great improvements. And there's great improvements coming. Now we're at 2.7, 3.0 volts. 20 years ago, we were at 2.3, 2.5 volts. It's, incrementally difficult to increase the voltage of a supercapacitor because it has such high capacitance, but it's happening. The cell, not only we are increasing into larger and larger cells by going into the hybrid technologies like lithium carbon, where we have cells as large as 20,000 farads. Also expanding in the packaging that is used out there. There's pouch packaging. There's snap-in and radials similar to electrolytics, as we all know. And there are modules and module assemblies that are being used and looked at by customers more than ever before. And then we have the temperature ranges where we're increasing now to 85 degrees C and looking to move to 90, 95 C in the years to come. And that is the end of the presentation of supercapacitors and energy storage. I thank you for your time. I look forward to your questions, and have a great day.
Thank you again to George Wansum for today's presentation. And thank you from both Cornell Dublier and Richardson RFPD for attending today's session. We look forward to you joining our other sessions in this series. Again, thank you for taking time to attend this event. Take care, and we will speak with you soon.